Last time, we introduced the storage and querying use cases of the Postgres extensions we are looking for, giving an overview of the GitHub repo that we created to help you follow along our educational content. Today, for part 2 of the PostgreSQL Maximalism series, we will look into document storage, showing you how to natively handle JSON on Postgres, and we'll also cover analytics, dipping our toes on open table formats in what is perhaps the first extension that turns Postgres into a viable alternative for your open data lakehouse needs. Let's get into it. So let's jump into our research Postgres extensions, starting with documents. Just for reference, we have 3 examples of non-Postgres document databases. We've got RocksDB, which is a key value store, ExistDB, which is an XML store, and MongoDB, which is well known for being a JSON store. Now, can we store that kind of content within Postgres? Yes, we can. So using HStore, which is a built-in extension, we can use Postgres as a key value store, one of the columns on our tables. We also can store XML using the native XML type. Postgres provides several functions to either to query your XML via XPath or to validate your XML based on a schema. And then we also have JSON and JSONB, which are also data types on the same level as XML, but they do not. Postgres does not provide a way to validate the schema, and that's why we installed pgJSON schema created by Supabase, which is a Postgres cloud provider. So let's get into a bit of a demo of how you can handle JSON directly using Postgres. So let's go into VS Code. Over here we have a SQL directory, and inside the SQL directory you'll find one directory per category of extensions that we are analyzing. Let's go into documents. We'll have first we'll load some data to play around with, then we'll look at how pgJSON schema can be used, and then we can look at how we can easily generate JSON responses from relational data or a mix between relational data and JSON columns. We'll be using Harlequin, which is a command line client, to test this out. So let's go into here. I have pre-configured Harlequin to connect to our Data Lab Tech database. You'll see a bunch of schemas for the installed extensions, and under public you'll also see a few tables and views, but we'll begin by creating our own. As we can see, there was no request table, so let's create that. So in here we are going to create a table with just 2 regular fields, ID and submit time, an integer and a timestamp, and we'll add 2 columns to store JSON documents, one for params and one for response. Okay, so we've created the requests table. Now let's insert some data into this table so we can play around with it. Okay, we have 10 records in here. Okay, let's make sure that these were properly inserted, and here we are. We have a bunch of JSON documents to test out. So let's go back into VS Code. In here you'll find a pgJSON schema script, which will contain queries to help us demo the pgJSON schema extension. First, let's create a schema to draw up our validation schemas for JSON. Let's go back into Harlequin. Okay, we have created that JSON schema. Now let's create a table within that schema for us to drop two schemas, one to validate. So we'll store schema ID. We will store the column name that we are validating, so this will always refer to the request table under the public schema, and then we'll store the JSON schema. Okay, we have created that same table, this time for storing JSON schemas. And now let's just insert two schemas, one for the params column and another one for the response column. So as you can see, we have a schema for params, which has a user ID of type integer, an action, which is a string that can take only these values, an email, which is a string that should be formatted as an email, and a bunch of other fields. And then we have the same thing for response, for the particular structure of response. Okay, so now that we have the schema, we can check whether these two schema are valid, with JSON schema is valid. So let's query these entries and check whether they are valid, and yes, they are valid JSON schemas. And now let's create a trigger, which is one way to handle this. Let's create a trigger. We could also just create a table with a check, but that won't allow us to update the JSON schema from a UI or some client. We'll have to alter table and, you know, change the schema in line with the table. If we do it this way, then we can just validate with the trigger and keep the schemas stored on a separate table. So this trigger will validate the schema, then it will get the schema selected into a variable, and then we'll check whether the schema the JSON stored on each column matches its corresponding schema. So if you notice, we do this twice, one for params and another one for response. If there is an error, we'll raise an exception, and I will demo that out in a second. So let's run this. So it seems that Harlequin doesn't like dollar quoted strings, which is what this is over here. We could go in here and just replace this with a string, but we'd have to escape everything. So instead, let's just copy this over and use pgcli instead. We can load the environment variables. Let's make sure it's been loaded. Can we run pgcli and paste it over here? As you can see, the function for the trigger has been created. And now let's also create the actual trigger, which is just before insert or update. It will always validate your schemas and validate the JSON columns as well based on those schemas. Okay, so we have it. We can go back to Harlequin, I guess, and now let's try to do something that is invalid, and let's do something like updating our schema with properties. So we are changing the schema itself, and we are updating status enum with a 10, which is it should be an array, so it will be invalid. Let's try to run this. Okay, let's confirm that the change was applied. Yep. So in here we have an example of a JSON field selection query. And so if we try to insert a valid response into our original request table, it should validate the schema, and because the schema is now in an unstable state, there are some errors, it should raise an exception. So let's, yep, and then there we have it, invalid schema definition, function validate request JSON at line 19. Okay, so now let's fix back our JSON schema. There we have it, and let's make sure the changes applied. Yep, and now let's try to insert the same documents we did before, and now we can successfully insert it without an issue. Let's try something else. Let's try, for instance, to insert an invalid action param and response status. So in here we have a delete account param which is invalid according to our schema, and then we have a warning status which is also invalid according to our schema. So you can see params does not match definition in JSON schema, it fails with the first record. Now let's try to fix the action. Let's change it to reset password, for instance, and run it again. Okay, so now the response does not match the JSON schema as expected, and now if instead we just replace warning with success, we'll be able to insert without an issue. So if we try to instead update an existing record setting delete account as the action, we'd get a similar warning, and if we try to do it for requests, it should be the same thing. But actually warning is an interesting status that we like to use, so let's add that to the JSON schema, and so we can just update the JSON schema for requests and use this JSON b set to set the schema under properties status enum. Let's just select the existing enum and append the warning status for response only. Okay, there we go. If we look at the enum now, we should see a warning as well. Now if we update the status with warning, it should be successful. And we can look at our final data, and this is what we have. Just a note, in Harlequin it will assume that every JSON will have the same fields, so you get something like email none over here, which is not really what Postgres is returning. Postgres is not returning an email or a name location, and we can repeat this in pgcli just to make sure. And as we can see, there is no email or location for the first record. This is just an artifact from Harlequin. So this TUI is kind of interesting, but it also lacks some features for Postgres yet. So So let's go back into VS Code, and in here we'll look into JSON generation. So first, let's say that we'd like to select a subset of our data for this time period. So if you run it, we get 7 records. And then let's say that we'd like to return this as pure JSON. We could do something like row to JSON, which will convert these rows into JSON. Then array ag will aggregate those rows into an array. Then array to JSON will convert everything into JSON, and this will return a nice JSON array ready to serve on your web app. And so this is it for the basics of how to store documents on Postgres. There's a lot more to learn, and you can check it out on Postgres documentation, but the goal of this video is not to go in depth into that. It's just to present ways to store different kinds of data and to query it using Postgres. So we're going to move on into analytics. So let's now get into analytics. Just for reference, we've got DuckDB, which is an in-process database built for analytics. It's similar to SQLite, except it stores data in columnar format. We've got Redshift by Amazon, BigQuery by Google. We got Databricks, which is essentially the parent company of the Lakehouse architecture. And we've got Snowflake, which is also a well-liked service within the data engineering community. So now turning our attention into Postgres, we collected extensions that could help us out store data in a columnar format and support analytics tasks. We found out columnar, which is by Hydra. Then there is PG Lakehouse, but it's been deprecated. This was created by ParadeDB, initially using Apache Data Fusion, which is a query engine based on Apache Arrow. This was eventually replaced by PG Analytics, which focused on using Apache Iceberg instead. Very recently, PG Analytics was itself deprecated in favor of integrating everything into PG Search, so kind of like what Elasticsearch does, because ParadeDB is essentially a search extension for Postgres, so they probably decided to focus on that. There is also PG DuckDB, which is the official DuckDB extension for Postgres. This was developed by Hydra and MotherDuck. It integrates with MotherDuck. However, you don't have access to querying DuckDB directly using SQL without passing that SQL into a query. We went with a solution called PG Mooncake, which still uses DuckDB underneath for its analytics capabilities, but it stores data using the Delta Lake format. I believe they are meant to support Apache Iceberg as well, but I couldn't find any way to create an Iceberg table yet. PG Mooncake lets you write into Delta Lake, which is something that DuckDB doesn't allow you to do yet, although it does allow you to read from both Apache Iceberg and Delta Lake. I think they are still working to support writing into those formats. Maybe in the future it will become redundant to use PG Mooncake, but still PG Mooncake integrates quite well with Postgres. You don't have to call a function and pass it SQL within SQL to be able to query the columnar store, and you can still access your open tables, right, and copy those into your laptop and use, for instance, polars to load and analyze that data directly. So to me it's quite interesting that we can do this with Postgres already. One thing that PG Mooncake doesn't provide yet that I would like to see is a better documentation, because all the documentation you have is just a few tiny examples. As you can see, they talk about iceberg, but I couldn't find a way to create a column store using iceberg. They only have this using column store, which creates a delta lake. So it gives you a few examples just on how to create the table. It tells you about some concepts of how this is organized. So it uses part of DuckDB, but they store this directly using Delta Lake. Since Delta Lake can be read by DuckDB, you can still use DuckDB completely for the analytics tasks, but PG Mooncake will handle the writing. So it provides a Docker image. We also provide a Docker image with it installed. It lets you know that you can run it on Neon, which is a Postgres cloud provider. It tells you which types of operations you can do. Oh yeah, they tell you how to set up access to S3 buckets. Also it supports R2 and GCP buckets. I actually set up min.io, although it was not directly supported by this current version. There is an open PR, and I just went into the PR and downloaded that code and merged it manually and changed this create secret function, and it just works. So in the near future you should be able to use min.io without an issue. Then it shows you how to load data using either reading from Parquet, JSON or CSVs, and it shows you how you can check out the location of your column stores. If you are storing on S3, you'll be able to find the bucket here, and you can just go into that location externally and copy it to your laptop and work on top of it, or just access it directly from polars. They also talk a bit about limitations. There are data types that are not supported, but overall for its target requirement, I think they do a fairly good job, although like I said, the documentation is a bit limited still, but I think they do a good job, and this is quite enough to get us started. So first let's go into VS Code. As usual, you will find a subdirectory within SQL for the category that we are now looking at. So let's go into analytics. Bit of a heads up, you'll need to disable the timescaledb extension before you can use PG Mooncake, otherwise there will be some incompatibility issues and you won't get any warnings that are indicative of why that is happening. So let's first do that, and today we are using pgcli. Okay, so we dropped timescaledb and we can now, PG Mooncake was already loaded, so we can now take a look at the code that we have here. So before anything else, we should replace this create secret function if we want to be able to work with min.io. This will just add URL style parameter. This is already supported in a PR in the C++ part of the extension. This didn't exist. I just created a replacement and patched the PR into this instance of PG Mooncake. So let's copy this over. Okay, and we replace the function. Now let's go into data. In here we'll be able to, you can drop the secret just to make sure it doesn't exist. Okay, so now let's create a secret with the function that we altered. So this is essentially your username and password, the endpoint without HTTP or HTTPS specified, because we do it using this parameter. We're not using SSL, and the URL style parameter, which is one that we added to make it compatible with min.io. So let's copy this over. And there we go, we are able to access our min.io instance. Let's just go into min.io really quickly. So we are running an instance of min.io, so it should be port 9001. We are running an instance of min.io, data lab tech and data lab tech as password, and in here you'll find the lakehouse bucket. I already have a few trials over here, but we'll keep these for now. But we should see new entries appearing over here. And let's go back into VS Code. So next, what we do is we alter the database to use the S3 lakehouse as default storage location. We can set it database wide, but we need to reconnect our session to make sure it's active. So we can essentially just run this alter table, and then to make it active in this current session we can just do it like this. Now we are using a lakehouse schema to drop all of our external stuff. First, let's create a table to store some YouTube data. This is available on Hugging Face, and Read CSV from Mooncake can load datasets directly from Hugging Face, and that's what we are going to do now. So we just created this YouTube table under the lakehouse schema. So you'll see a lakehouse schema over here, and if you list the tables for this lakehouse schema, you'll see there is a YouTube table. Now we just insert into this table using every field from this CSV. This should match the previous table. Just do that. Okay, this will take a while because it will download the dataset and load it into the YouTube table. And after 17 seconds we are done. It's not a huge dataset. Now we are going to create a similar table called YouTube, but this time on the public schema, and we'll load it with the same data that we loaded into our column store. So we'll have a row-wise version and a column-wise version, and also we add a primary key. This is not supported by the PG Mooncake, I believe. Let's copy this. It should take a while. Okay, So now that we've done this, let's get into a few examples of what kind of analytics queries we usually want to run on top of this stuff. So a very simple one is just a count. So you can count the number of records or the distinct videos that we have on this dataset. So the dataset is a dataset with a timestamp. It's only for trending videos, and you have information about the same video for multiple different timestamps. So it's essentially a bunch of time series for each video. So let's look at the count first. We've got about 1.5 million entries. Let's see how many videos do we have as well. We have only 11k videos in total. We have about 100 times the stats for each video. Now, one thing we can do is just count the number of entries of distinct videos per month, and in here we are starting to group by and do types of computations that we usually do when we are doing analytics. This will give you the month start with this date trunk, and it will give you the number of distinct videos that are trending in that month according to this dataset. Another thing we can compute, and I'm going to switch back to VS Code for this one. Another thing we can compute is the number of average likes and dislikes for trending videos per week. So this is a bit of a more complex query. Well, it's still a simple one, but what we are doing here is because we have statistics that we can have more than one entry per video on the same week. We are first selecting the last entry, the most recent one for a given week, and we do this by computing this recency over here. I'll just copy over this one so you can check out what it does on pgcli by its own. So essentially, I don't know if this will be too much data, but essentially you have a recency for a given YouTube video. As you can see, for the same week we'll have multiple records. We are interested in getting the most recent one. We are partitioning by YouTube video and week, and then we are ordering by timestamp, and then we are computing the row number over this partition. And so every time we filter by recency equals 1, it's like applying a limit of 1 over this group. This is like a group, and then we can effectively do our computations and compute the average likes and the average dislikes. We are rounding this to integers over here. So let's copy this over to pgcli. Okay, and there you have it, number of average likes for trending videos per each week. We are going to test this query on the columnar store versus the row-wise, the regular table, just to to actually look at the number of transactions per second that can be run on a columnar store for this type of analytics queries versus a regular row-wise store, and it will become pretty clear why a column store is useful for analytics. So let's go back, let's continue into the second benchmark query we have over here. For this one, it's a multi-stage query with many steps and a few unions over here. What we are doing here is comparing the view counts of trending YouTube videos with a higher share of likes than dislikes versus those with a lower share of likes. So what we do is, first we rule out the extra data and keep only the last entry per video per month, most recent one, and this is what we are doing here. And at the same time we are computing the likes share, which is the number of likes dividing by the total number of likes plus dislikes, and the dislikes share. And then we compute a few statistics over the likes share for all entries. We filter for only videos that have a lower likes share than dislikes share, and also a higher likes share than dislikes share. What we use here is a filter to make sure that we only compute the average of likes share or the percentiles for videos, in this case with a lower number of likes than dislikes, or lower likes share. And if you never done this will let you compute the median within a given group. And because percentiles require that your input is ordered, because it's a positional way to compute a statistic, you can use this within group order by views, and this means that we are computing the 50% percentile or the median over the views, right? And then we just do a union, so we can have a month start, a subset, and the statistics. So let's copy this over into pgcli and look at the output. Okay, there we go, and this is the output. So we'll have a bunch of statistics per month. Okay, we have 3 entries per month where we get the statistics for all videos, for the ones with higher likes than dislikes and lower likes share than dislikes. And we have very few videos with only a higher number of dislikes, and we get the average likes share, which is usually a lot higher, 95% for instance. We get the percentile, 10% percentile, we get the median, and we get the 90% percentile. So now let's go into VS Code again, so I can show you something. So over here on this subdirectory called pgbench, what we did was reproduce these queries Q1 and Q2 for the columnar storage, so the same ones that we are running here over the Lakehouse YouTube table, and the relational table, which is the public YouTube table. So we get something like this for columnar, the same query for relational, and another query, the second one for columnar and another one for relational. And then we have run benchmark script, which essentially just runs pgbench with each of these scripts for 30 seconds. It tries to run as many transactions as possible, so each one of these will be a transaction and will let us know how much faster using columnar storage for these two queries is than using the traditional row-wise storage. So let's go into the terminal, and this time let's go into our SQL Analytics pgbench, and let's run the benchmark. Okay, and we are done. So let's go look into the output of this. We are particularly interested in the TPS, which is transactions per second. We are interested in comparing the columnar version of each query, so Q1 for columnar and relational. So as you can see, for query Q1, we can run about 4.5 transactions per second of this query on the columnar version, but on the relational version we can only run 0.76. So as you can see, and this is not too much data, it's just 1.5 million records, we already see some significant speed up by using a columnar store. And for Q2, let's see, we can do, in the columnar store we can do about 1.5 transactions per second, and in the relational store again we can do a lower number, although the difference is smaller than the previous Q1 query. For Q2 we only get 0.7 transactions per second. So as you can see, it can be quite beneficial to have a column store, and on top of that you get all the good stuff from open table formats. And you can, if you are running a company and you want to have some central repository, data lakehouse for your data, and you already have a Postgres instance that can run pgbench. If it runs on Neon, you're set. If it runs on your VM, you are also set, because you can install it yourself. Otherwise you have to check whether pgbench is supported. It usually isn't, because it's very new, but if you can use it, you'll very easily be able to share this data with your data science team, or and keep it centralized in Postgres as well. Actually, I also include a Jupyter notebook to demo some of this stuff. So let's go into our notebooks over here. This is running with UV, so you can just run UV run Jupyter Lab or notebook as you prefer. Let's take a look at the notebook we've got here. So for demoing how to access Delta Lake, we'll use DuckDB running in Python. We use .env to load our environment variables, and we set up a few defaults and the Postgres connection string over here. We also set up the connection to min.io. We use localhost because we are outside of Docker. And then we can go into pgbench and we can retrieve the storage path using SQL. So for this we use pandas. We just select the path from the column stars table, where the table name is YouTube, which corresponds to our lakehouse YouTube table. And this gives you the latest entry. You'll be able to find it here as well. So this is the one that ends with 128. You go here, you should be able to find that same entry. And here we have it, 3496128. 3496128, it's the same entry. Now we can just create a connection to DuckDB. This is just running in memory, and we create the secret in a similar way that we do on pgbench, and then we can run a delta scan over the table path that was returned in here, just to count the number of records. As you can see, we are able to do it. So now let's go into some pros and cons, a bit of a general overview, and let's compare, for instance, JSONB for document storage versus MongoDB. So most stakeholders across the business understand SQL, but the same isn't true for the MongoDB query language, and I've seen this firsthand, definitely. MongoDB supports schema validation out of the box, but Postgres needs PG JSON schema. Both do support it, so it's just a matter of wanting to install this extra extension or not. And it's harder to ensure data integrity with MongoDB without foreign key constraints, which you have on Postgres and relational databases in general. Your referential integrity does not exist, which leads to orphan documents. Again, I've seen this happen in data science teams that were using MongoDB. There's some events happened that led to the data being backed up and restored again, and as that was happening, few foreign keys, which were really foreign keys, were just the records they pointed to, they were lost. So this is something that you can ensure by using Postgres very easily. And I've seen a trend of data teams switching from MongoDB to Postgres or relational solutions because of stuff like this, really. Then we have PG Mooncake versus, standalone DuckDB. DuckDB is an in-process database, so you really don't use it as standalone. You might use it through the command line, but you usually use it through Python, perhaps. So DuckDB cannot write to Iceberg or Delta Lake, at least for now, but PG Mooncake can, and with PG Mooncake you get Delta Lake table storage, which is accessible externally by Polars or Spark or whatever can read Delta Lake. And you still get DuckDB vectorized analytics queries to ensure a high performance, so it's really an interesting solution right now because of that. I believe it is ranked among the fastest analytics engines, and here we go. So PG Mooncake, on their homepage, they claim it's top 10 on ClickBench. I think I checked this out before and it was actually higher on the ranking, but if we go to the ClickBench ranking and you look for Mooncake, you'll see that PG Mooncake is ranked quite high on the ranking still, although we can find DuckDB over here, standalone version. Let's see, we have Data Fusion over here. Let's see, we have ParadeDB over here. So yeah, if you go with PG Mooncake, I believe you will be very happy with it. It's quite efficient. It doesn't give you too many headaches because it's just regular SQL on Postgres, and you still have the ability to share those external Delta Lake tables with your data science team if you want to. So next time we will continue with time series management, showcasing a simple anomaly detection approach, and also we'll cover vectors in AI, where we'll demo a movie recommender system that gives you an overview on the types of movies it picked out for you. I think the next one will be quite interesting, and you can find the unedited research notes for this series as a blog post at datalabtechtv.com, and also take a peek at the upcoming content for the following parts. Don't forget to drop a like and subscribe for all things data.